Hello everyone, welcome to Jinghua Education. I'm Steven. In this video, we're going to talk about the introduction of Exponent Part 11, which is how to do application questions of exponent expression or exponent equations. Okay, so in Part 10, we did a question, and then it's relatively simple. Part 10 is just help you to understand and then just encourage you, don't be afraid of these kind of questions. The part 11s, I will show you actually what this look like. It's a hard questions. Okay, so I can guarantee you it's the hard part only about the numbers. It's nothing about the logic. Logic is still fine. It's very easy, very understandable. Okay, so let's see questions here. Over time, a sample of radioactive isotope was lost mass. Okay. When you reading these kind of questions, especially for the exponent questions, there aren't too many special type. Okay, so you're gonna see Newton cooling laws, like hot water become colder, radioactive, and then populations, and then bacteria, and that's it. That's all you're seeing. You'll see these things all over the place. Okay, so when the hot water, like 100 degrees, put in the room temperature, is getting cooler very fast. For example, like every minute it's drop like 10 degree. But when they actually closer the room temperatures, it's dropping slower and slower. That means, for example, maybe take like half hour from 21 degree to 20.8 degrees, something like that. So because it's close to the room temperature. So that is, we call them Newton cooling law. And then normally bacteria is increasing, and then bacteria is growing, and then every how many hours is being doubled himself, and then the human populations is getting bigger as well. All right, so and then radioactive things is getting lose their radioactive abilities. So like this radioactive isotope is losing their mass, something, and then you're gonna see these things all over the place. So don't be afraid. They only these few tabs. I don't see too much questions with something else examples. So yeah, don't be afraid. Exponent is nice. Okay, exponent is not that hard. Let's just focus on the question. Okay, so we have isotopes, radioactive, blah blah blah, and then we have half-life. Okay, the half-life and the doubling times. I'm going to give you brief introduction of this. In grade 11s, I have very detailed explanations about what is half-life and what is doubling times, and I will show you how to calculate that and how to use them. Okay, what is double half-life? Half-life is the time. It's the time measured. So how long is the take to something to become his half of his mass? That's the half-life. It's especially for the radioactive things. The radioactive content is getting smaller and smaller, and then by the exponential rate. Okay, so it's how long it takes to become half of his mass. This is half-life. So in these questions, half-life is 5,730 years. That means carbon-14 is become half of his mass in 5,730 years. Okay, that's a long time. However, that is the mean method, the paleontologists found out how many years old of the like a dinosaur's bone something. Okay, so as I'm off the topic right now, just let's focus on the math. Okay, doubling time is simple. Doubling time is the same thing. It's a doubling time is the time, right? Time taking what? The time take to something to grow to be doubled. For example, you save like $1,000 in the bank. How long times take you $1,000 become $2,000? That is doubling times. Okay, so again, I will talk more detail about these kind of things in the grade 11 tutorials. Please also watch that if you like. Okay, so let's focus on here, right? Okay, we have 88 grams. That is initial mass. Okay, and then our half life is this one. That means the 5,730 years is become of his half. Another 5,730 years is of the half and the half, right? So the A is the mass of the isotope, and then the T is the time passed, and that's it. So all we need to do just plug in numbers, and that's it. So what will be the mass, the carbon 14 sample in 2000 year? Okay, so we're looking for the mass, right? So we have 2000 as year, which is the time. We put 2000 on the top, in replacing the t, 2000 over 5730, and then to the one half, and then 88 times 8, that will be our a here. Okay, the number is scary, but actually you can punch this into your calculator, and it's just a number. Okay, 88, half is zero point 0.5, right? 0.5. And then 2000 divided by 5730 is equal to 0.35. I use my calculator, so you can use yours. Okay, and then zero point 0.5 to the power of 0.35. Yeah, normal calculator can do that. So you're looking for these things. Okay, this button here. So y to the power of x, you punch zero point 0.5, you press these buttons, and you enter 0.35. You're going to find out how much is 0.35 to the power of 0.5 to the power of 0.35, which is equal to 0.785. And then times 88 equal to 69 is a gram? Gram, yes. Okay, it's a gram. So that means after 2000, the carbon 14 from 88 grams becomes 69 grams. Does that make sense? Yes, because what? After 5,000 years, it's become 44 grams, right? So it's not enough for the 5,000 yet, 2,000. So it's not to the 44 gram yet. Okay, that's what the half-life means. Okay, the first one, A, is done. The B, what will be the mass of carbon 14 sample in 5,730 years? Hey, that is what? That is half-life, isn't it? So half-life, that means one half-life later. That means exactly 5,730 years. It just become half. So 88 gram become half is a 44 grams. Done. We don't even need to calculate this. So if we want to calculate, how do we do that? It's a 5,730 divided by 5,730 equal to 1, right? So 1 half to the power of 1 equal to 1 half. So 88 times 1 half is 44. That's it. Okay? It's not hard at all, right? Good. All right, the next one. So if the mass of the sample is measured by 10,000 years in the futures, what will the percentage of the original mass remains? Okay, so again, don't panic. I know this wording is throw you off. You don't know what to do, and then you say, "Wow, what that means? What's the proportion? What's the percentage means?" Okay, I will show you that. I just remove that to make some space. Okay, so 10,000 years. Writing 10,000 instead of t. Put 5,730 in the bottoms, and then 1 half. We still do the same thing. Okay, that means after 10,000 years, how much mass we have, right? Good. Let's put these things here. 10,000 divided by 5,730 equal to 1.745. Okay, equal to 88 to the 1 half, 1.745. And then if we're doing the powers button again, regarding 88 times 0.2, 0.30. Okay, good. That means 1 half to the power of 1.745 is 0.30. Okay, times 88. So we don't even need to times it. Why? Because we are not asking for how much is left. We are asking what? What is the percentage of original mass remains? Percentage of what? Percentage of remaining divided by original. Remaining is how much? 88 times 0.30, right? So original is how much? It's 88. So we cancel out. It's zero point 0.3, which is 30% of the remaining of the original. That's it. That's all we want. Okay, if you like, you can multiply 88 by zero point 0.3 and then divide by 88 again. You got exactly same answer. That is the percentage. Okay, good. So again, don't be afraid of these kind of questions. It is nice questions and then it's easy to do. Just plug in numbers and then use your calculator. You can do your work. Okay, so I hope you enjoy the videos. If you like, please subscribe. If you have any questions, please comment below. I will answer your question in my next video. Thank you for watching.